Right. Practical 4. 4. Right. Okay. So you had something. Meals, you had something and refreshed. Okay. So I hope online students are also refreshed. And now I'll be continuing straight until the end, right? Until the end, we'll be continuing straight, right? So again, make yourself comfortable with the class because we are going to continue until the end of the class, right? So I have planned to do 30. So let's see how it changes. Yes, how it changes in the sense now if you do these things faster, if you grab these things faster, it'll be a little bit earlier than 2:30, and the opposite is also like that. Okay, 1:15 now. We'll start. Next one. Okay, heading, write down determination of relative density. Determination of relative density of a liquid using Hare's apparatus. Using Hare's apparatus. Using Hare's apparatus. Give me 1 second. Right. Okay, now to determine relative density, listen. To determine relative density of a liquid, there are two methods. We have two experiments we have, right? One of the experiments was the previous one using YouTube, right? And this is the second one using Hare's apparatus, right? So the respective theory part is we have something called a setup called Hare's apparatus in our labs, in school lab, right? Have you seen Hare's apparatus? No. The respective theory part is this. Respective theory is we have something called Hare's apparatus. It is something like this. Look at the board. This is a setup. Huh? This is a setup. And here there's a valve. And then these two tubes are dipped in a container like this. They are dipped inside a container. They are dipped inside a container like this. Right. Here, there is one advantage over a YouTube. That is we have two different containers to put liquids in. So therefore, this is especially designed to find relative density of two miscible liquids. Okay? Two liquids are not going to be in contact. Now, when we insert a liquid here, right, and when we insert a liquid here for these two, right, after inserting the liquid, then what we have to do is we can open this valve from here, right? After opening the valve, we have to suck air out by mouth, right? There are two methods, by mouth or by using a syringe. But for by using a syringe, the last time no marks were given because usually how we do is we are releasing this and sucking air out by mouth. Right? Then we well at thin, right? There are cut කට තියලා එයා එක පම්ප් කරලා එළියට දානවා. පම්ප් කරලා එළියට දානවා කියන්නේ මෙතනින් අපි අදිනකොටම මෙන්න මේක දිගේ මේ ලික්විඩ් එක එනවා. Right? Remove this valve from here and suck this air out by mouth. Then once we do so, this liquid here rises up through this tube, and the liquid here also rises up through this tube. It will be something like this, which means what we are doing is, now initially this part is at atmospheric pressure, but if we suck air out, that pressure reduces. When pressure reduces, the liquid rises from high pressure to low pressure. Right? Sucking air out means the pressure will be reduced from atmospheric pressure. Right? Because higher number of air particles means higher pressure. Right? If you are doing chemistry, you will know it by now. Now, for us also we have those kind of gas parts in thermal physics. Right? So now we are here after mechanics. So just know that lesser the volume of air, lesser the pressure at the same temperature. Right? That's the thing. I just started, take down the heading, and that's it. I didn't ask to take down anything here. That's what. Okay. Okay. So now, once this air is sucked out, listen again. Now in Hare's apparatus, we have one curved tube like this. One curved tube, and these two parts are vertical. Now these like an upside down U tube. But here there is another mechanism with a valve. Right? And these two are two beakers. They are two beakers. And we can put the liquids that we need to consider here into the beakers. Right? And opening this valve, we can suck air out using by mouth. Then these two rises up along the limbs. Right? Okay. And again, we have to close the valve. Once it is closed only, it will be still like this. Otherwise, if it is open, again it is coming to atmospheric pressure, it goes down. Right? So therefore, we have to just open it, suck air out, and close it again. Right? Now the setup is like this. Setup will be like this. Right? Look at here. Now this is open to atmosphere from these ends. So P naught tax. Here also P naught tax, because these beakers are open to atmosphere. Right? And let's assume the liquid height here as H1, and the density of the liquid as ρ1, and the height of the liquid here as H2, and the density of the liquid as ρ2. Right? Now, here this is an air medium. This is an air medium. Pressures at any point of an air medium is same or different? Pressures at any point of an air medium is same or different? They are same. Right? Now, this is a closed room. Pressure at any point of this room is same. That is an air medium. Atmospheric pressure. Right? So in air medium, pressure doesn't change. That is same. Now this is also an air medium. So that is same. I'll assume the pressure at air medium here as P dash. Let's say P dash. Right. This is the theory. Look at the board. Now we can write P dash starting from left side here, left limb here. This is P naught. And we know pressure difference through a liquid column is given by H rho g. Downwards plus H rho g, upwards minus H rho g. Now P naught is here at this same level. Now we have to go up. Going upwards means minus H rho g. Then here minus H1 rho 1 g equals, now we are at this level, which means P dash. Right? Same thing using the right limb. This is at P naught. And we can go up until we reach the gas medium. Going upwards means H2 rho 2 g. Now again, that is at the gas medium. Now these are two equations for same P dash. No? So therefore these two are equal. 1 equals 2. P dash equals P dash, which means from this side P naught minus H1 rho 1 g equals from the other side P naught minus H2 rho 2G. Right? P naught to P naught cancels. Minus H1 rho 1G equals minus H2 rho 2G. G to G cancels. And minus to minus also cancels. Right? So what remains is H1 rho 1 equals H2 rho 2 again. This is called the principle of a Hare's apparatus. Right? So the advantage of using Hare's apparatus is it can be used to compare two miscible liquids. YouTube එකෙන් mix එකක් කරන්න බෑ. Right? For YouTube it should be two immiscible liquids. For Hare's apparatus, any two liquids, it doesn't matter whether it's miscible or immiscible because they are on two separate containers. They are in two separate containers. Clear? Right? That's the theory part. Okay, as a theory, take this down. As a theory, take this down. I have to go far. Now that so exactly in front of here, Amrita, it's Tamil. It's open. No, I don't think yogurt drinks are. Yeah. Yes. That's close. Then to where you went? I see. Right. Duplication road. Then you didn't find anything for yourself. Right. Finish. Take it down. Take it down. Finish. What about the online students? All good? Any questions? Finish. Okay. Look at here. Look at here. Now this is a setup we have in the lab. See, now we have this in the lab. Now again we are taking the Hare's apparatus setup. We are taking the Hare's apparatus setup. And for these two containers, we have to add the two liquids that we are going to compare. Right? We are adding two liquids that we are going to compare. Okay. Any two liquids can be used. Any two liquids can be used. So here also I will consider coconut oil and water. Right? Any two liquids can be used. That doesn't matter. Right? With the popularity, I'll be using coconut oil and water again. Any two liquids can be used because This is valid for any two liquids. Any two liquids. Right? So as one of the materials, we need Hare's apparatus. That's an apparatus we have, Hare's apparatus. And this side, let's say, I have inserted oil, right? Let's say an oil. And this side, I have inserted water. This side, I have inserted water. Right. Now, once these two are put into the containers, listen, this part is important. Once these two liquids are put into the container, right, into containers, what you have to do is we have to remove this valve from here. This is a valve. This is a valve here, right? So we have to remove this valve from here and we have to suck some air out, right? Not all, suck some air out until this rises up and close the lid again. Close the valve again. We have to close it firmly. If there are leakages, again the liquid goes down. Because if there is a leakage, again the pressure changes inside. We have to keep the pressure constant. So tightly keep it after closing, and once it is sucked out, you can see this liquid rises up along the length, right? At the same time, both rises up, and this one also rises up along the length, right? Now in Hare's apparatus, to see these liquid levels properly, to identify these liquid levels properly, another index is used. Index in the sense, we are using a bent pin. We are using a bent pin. A bent pin or a needle. A bent pin or a needle. And that pin is connected to here, like this. That pin is connected to here like this. The purpose is, let me draw here again. The purpose is, without looking from the top, now like this and like this. Without looking from the top, they are called index, index. Without looking from the top, now this is with a movable rubber band. Movable rubber band. We can take it up and down easily, right? So once this is closed again, we are taking this until it just touches the water surface. Right? And for the other one also the same. And here also we have to have a scale. And in some Hare's apparatus, listen, in some Hare's apparatus, the scale is already mentioned in the board. In some, that is mentioned already in the board. And if not, we have to use meter rulers as the previous one. Right? Let me draw meter rulers. Now, when we are using meter rulers, there will be meter rulers here. Half meter rulers. Meter rulers can half meter rulers like this. And here also. That is to take readings. Meter rulers. Right. Take it down first. We didn't write materials. Okay. Next heading. Apparatus and materials and apparatus. Next heading, materials and apparatus. About using pins, this is the logic. Listen. About using pins, the logic is this. Now, when we look through the glass container here, we will see it through a refraction. There's a refraction of light due to glass. So therefore, there is a possibility of having a deviation of the reading we read. Right? There's a deviation because of the refraction. So therefore, this precaution is used. मैं पिन එක ගන්නට මෙහෙම පාත් කරලා තියෙනවා. right? පින් එක පාත් කරලා තියෙනවා. ඊට පස්සේ මේ රීඩින් එකයි මේ රීඩින් එකයි ගන්නවා. see? Now this is on air නේ. This reading is on air. On an air medium. So therefore, this reading can be taken. Let's say x1 or x cube. Let's say x, right? The x1, and may reading net gun now. Let's say x2, and this is starting point of the needle is also at air medium. Make it gun. Let's say x2. Make it gun. y2. Sorry, x2 y1, y2 kill them. See, y1 and y2. And then after removing these water containers, we can measure only this part freely, without any refraction, without any disturbance from refraction. That's the may part. That's the benefit. That's the benefit. That is how it increases accuracy. Otherwise, if you try to measure it at once, there will be errors because of refraction. There are errors. There are errors because of refraction. That is why a pin is used. Right? The pin එක විතරක් වෙනම measure කරනවා මේක අයින් කළා. We can remove after the experiment. After these readings are taken, we can remove these water containers and we can measure this height of the pin later on. We can measure the height of the pin later on. So let's assume, look at here, let's assume this rho O, rho W. And let's assume height of this part is this part. Let's say height of this part is HO dash, right? Listen. And height of the pin here is, let's say, H1. No, HO here. Let's go the other way. HO and HO dash. See, HO and HO dash, let's say. Right? And this side, let's say, height of this column here, let's say HW, right? And height of this part of the needle is H dash W. Now, when I need the total height, it can be obtained by H0 plus H0 dash. This is HW plus HW dash, right? So that is higher in accuracy. That's the benefit we have. That is higher in accuracy. That is higher in accuracy because we have omitted the impact from diffraction. So likewise, if that is possible, we will go ahead with that. Right? Then capillary tube එක ඇතුලේ තියෙන එකක් නම් අපිට එහෙම කරන්න බෑ. හැබැයි දැන් මේක අපිට ඇඩ්වාන්ටේජ් එකක් තියෙනවනේ මේක තියෙන එළියේ තියෙන කන්ටේනර් එකනේ. ඒ හින්දා මේ වැඩේ කරනවා. To get more accuracy. Is that clear now? Right? Okay. Finish taking down? Oh no, we didn't write. Apparatus and materials and apparatus. Okay, under that, first head in materials. Under that, first head in materials. So under materials mention, first one, Hare's apparatus. First one, Hare's apparatus. Hare's apparatus. Hare's apparatus. Next one, two liquids within brackets, oil and water. Two liquids within brackets, oil and water. Next one, two half-meter rulers. Two half-meter rulers. Two half-meter rulers. Next, two bent pins. 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 Right? Okay. Next heading, apparatus. Next heading, apparatus. Take it. Sorry? Immiscible liquids can be put into U-tubes only. Immiscible means not mixing. For both, these two liquids are not in contact. These two liquids are not in contact. Any two liquids can be used. So especially we are using Hare's apparatus over U-tube for miscible liquids. Miscible නම් ඉතින් මේක ටිකක් ලොකුයි YouTube එකට වඩා මේ setup එක ලොකුයි. මේ වගේ ලොකු setup එකක් use කරන්න නැතුව YouTube එකෙන්ම වැඩ කරගන්න පුළුවන්. මේක ටිකක් විතර ලොකුයි මේ වගේ setup එකක් මේක. Right, this is high in size compared to the YouTube. Is it compulsory to use immiscible liquids? No. See, I told you any two liquids. Any two liquids. Right? Any two liquids. Finished. Finished. Okay. Now, with this same apparatus, now we are applying this theory. Now, this is a theory with the Hare's apparatus, right? So, therefore, so let's assume pressure at here as P dash again, and atmospheric pressure as P naught. Atmospheric pressure as P naught, right? So, we can apply the theory like this. Look at here. You can apply the theory like this. From left limb, P naught minus, now we can go up, HO dash plus HO rho OG. Let me write somewhere here. See, same theory. P naught minus, when you are going up, minus HO dash plus HO rho OG equals, other side, P naught minus HW dash plus HW rho WG. Right? Simplify this. Once this is simplified, you can take this up to here. HO dash plus HO times rho O equals H dash HW dash plus HW times rho W. Right? Okay. Now we are going to plot a graph again. Right? We are going to plot a graph again. To plot the graph, these heights should be changed. To change heights, what we do is, we can, listen, this is a different one, very important one. We can slightly open this valve again and let air comes in. Once we let air comes in, these two goes down and again closing. Again letting air comes in and again closing. So likewise, we have to take 6 different readings. Right? Then mega I open කරන්න මෙයා පල්ලෙහාට යනවා. මෙයා atmospheric pressure එකෙන් pressure එක ඇතුළට එනවනේ. From atmosphere, it will get some pressure inside when the valve is open. So therefore it goes down again. It goes down. Now let's say initially it is at 6 centimeters and 4 centimeters. And if I open it again, it goes down. Then it will be like 5 centimeters and 3.5 centimeters. So likewise, it goes down. Such 6 readings should be taken to plot the graph. Such 6 readings. Right? Initially, we are sucking and closing. And then when the experiment is done, we have to open it 6 times and get 6 readings. Open it 6 times and get 6 readings. Right? Is it clear? Now, I'm going to create. Now, what's the purpose here? We need relative density of the liquid. Since we need the relative density, again, I need to create rho over rho W. To create rho over rho W, do a simplification here. Do a simplification. See? Now, I'll be simplifying this equation here. Need to create rho over rho W. See? Then HO dash plus HO times here rho O over rho W equals, from other side what remains is H dash W plus HW. These dash values are constant values, no? because they are the length of pins. Length of pin is a constant. Even though the liquid height changes, height of the liquid changes, length of pin is a constant. Length of pin is a constant. So therefore, variable is going to be what? HW. And from this side, variable is going to be what? HO. HO the variable. See? Now, we can simplify this like this. You can simplify this like this. Now, in this side, we have HO dash times rho O over rho W plus this is HO times rho O over rho W plus this is H dash W plus HW. I'm going to change sides. Subject HW. HW equals here rho O over rho W HO, right? Plus rho O over rho W HO dash, when this is taken to the other side, minus HW dash. Is it visible? Yeah, visible. Okay. Now, the term that we wanted to create is created already. Now we can identify the shape here of the graph. Now, this is my y variable, y, dependent variable. And this is the independent variable, x, right? Whatever it is as a product with the independent variable is the gradient. So this is gradient. And this entire part that is added after the independent variable is called intercept, C. So therefore, what we are getting is a graph of the shape, standard shape, y equals mx plus c. Our graph is y equals mx plus c, right? Now from this you can see gradient is again rho over rho w, that is relative density. කොහොම හරි readings පාක් කරගෙන graph එක ගහගත්තා නම් වැඩේ ඉවරයි. graph එක ගහගත්තා නම් if you can take 6 readings and if the graph is product, which means gradient is known. If gradient is known, relative density is known. Clear? Okay. Now, where did we stop? Materials. Okay, then apparatus. Next heading. Didn't you draw the apparatus? You draw, right? Apparatus killer. Okay, now apparatus is drawn. And below that, write method. Write down method. And starting from here, copy it down up to this point. Starting from here, copy it down up to this point. Starting from here, copy it down up to this point, y equals mx plus c, until the equation. Dylan, you have to take this down. Finished? This experiment is a little bit advanced compared to YouTube. YouTube is a very simple setup. No? YouTube is a simple setup. Simple in the sense there's nothing at all. Very simple. But here, the setup is a little bit advanced. Right? If we are dealing with two miscible liquids. This is the only option we have, so we have to go for it, right? Hare's apparatus. And we discussed the questions of Hare's apparatus in hydrostatics, right? So there the theory was discussed. I just recall the theory again today. Finished. Okay. So mention the method one by one. First point. Insert two liquids. First point. Insert two liquids to be considered. Insert two liquids to be considered. Insert two liquids to be considered. Into Hare's apparatus. Into Hare's apparatus. Into Hare's apparatus. And suck some air out. And suck some air out. And suck some air out. And suck some air out through valve by mouth. Through valve by mouth. And suck some air out through valve by mouth. And close the valve again. And close the valve again. And close the valve again. Right. Next point. Apply the principle of Hare's apparatus. Next point. Apply the principle of Hare's apparatus. Apply the principle of Hare's apparatus. Apply the principle of Hare's apparatus. Okay. Now look at here again. Look at here again. From above equation. Don't write, look at the board. From above equation. Right? Now if we plot the graph. Now the graph is y equals mx plus c, no? Mx plus c. It will be like this. Y is hw. And x is ho. Right? This is a mx plus c graph. And gradient of this graph will be gradient, let's say m of this graph is, according to the proof, rho over rho w, right? Which means if gradient is known, this is known, right? Once the graph is plot, that's the end of the experiment. Graph anything, that is just a matter of determining the value of gradient. If the value of gradient is known, relative density is known, right? Okay, start from here, from above equation, and then come up to here. Finish? Okay. Then write down here. Since gradient of graph can be determined, Since gradient of graph can be determined, relative density of liquid can be found, right? Since gradient of graph can be determined, relative density of liquid can be found. Relative density of liquid can be found. Relative density of liquid can be found. Right? Okay. Then again, as in extending diagram, remarks / important points. Remarks / important points. Remarks / important points. Remarks / important points. Okay, first point, first bullet, write down. Hare's apparatus can be used to. Hare's apparatus can be used to. Hare's apparatus can be used to compare densities of two miscible liquids. Miscible. Two miscible liquids. Within brackets, this is an advantage over YouTube. This is an advantage over a 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 YouTube. Right. Next point. Next point. A bent pin is used. A bent pin. A bent pin is used. A bent pin is used to avoid impact from refraction. To avoid impact from refraction. To avoid impact from refraction when taking readings. Okay, right. So that's it for Hare's apparatus. So that's the end of practical 4. That's the end of practical 4. And we are going to move on to our last practical for today, practical 5. So before that, any questions? Understood? All good? You? Online students, any questions? Quickly. Before moving on to practical 5, last practical for the day. Last practical for the day. Before moving on, any questions before erasing the board? All good? Last note. Someone please send the note to the chat. No, clear. Okay. For all of you, is it clear? Right? Okay then. Then we are moving on to the last one. In questions, what if a liquid other than water is used? Totally fine. Totally fine. I told you any two liquids, huh? Any two liquids. For any two liquids. Any two. Any two means any two. Water is used with the popularity. Right? Availability. Right. Okay then, let's move on. The last experiment, last practical for the day.